I know what he's doing. She's like, I hate you. No, it's not working.
That was my kneecap. There was the other one. My knee popped.
Ever since I put this up, I've been going, rah, rah, all right, you ready? Hurry up, hurry up.
Oh, yeah.
Oh.
Where the heck is it?
Hurry up.
Yes. Oh, okay.
Two. I'm getting 22.
But I forgot which one.
You just have a long Thanksgiving break?
Me too.
We got a new channel.
You got a new train.
Oh, I was like, have I been doing the wrong one? Yes. I don't know.
All right, y'all up here? Because I'm clicking. Everybody make a guess. A guess is better than no answer.
I decorated the book for all morning and invested. I'm so hungry. I didn't want to leave work.
Whoa, I was laughing.
We're smart, y'all.
Maybe we should go over it.
Probably.
Yeah,
We
let's do
should.
it.
We definitely should.
No, you got it right. I was just teasing.
Because I don't want to drop my clicker. I think I want to pour next week. I want to get out of that final.
All right, so you got E and Z, right? It's really easy. Right? Okay, just a couple things about the cycloalkenes. Remember that they're more stable as the cis isomers. They have made transcycloheptene, but it's only stable at minus 90 degrees C. It just, yeah, comes apart. It's chilling down there. That's right. Okay. When you get over 12-membered rings, the cis and trans are of approximately equal stability. 12-membered ring, remember, is called a cyclododecene.
I want to go.
When there's more than 12 carbons in the ring, the trans is actually more stable than the cis. But once again, people would say. Okay. All right, you got all that? Okay, we're gonna.
Can we get a house in the Philippines? Because I want to go. I'm so tired. 12 degrees Celsius.
Okay, elimination reactions mean that we're going to lose two atoms or groups of atoms, and we're going to make a pi bond. Okay, so what's a pi bond? No, pumpkin pie. It's p orbital sideways overlap. P orbital sideways. It's that simple. Okay, there are two basic mechanisms. There's going to be a two-step mechanism and a one-step mechanism. Okay. Okay, the first one that we're going to do is dehydration of alcohol. So what do you think dehydration means?
Taking out water.
Amen. You got it. She is here today. Yes, we're going to lose water. okay? And we're going to start with compounds that are alcohols, okay? So here is the OH that we're going to lose, and we're going to lose an H on a carbon that is next to it, the neighboring carbon, okay? You're going to lose water, and you're going to make a double bond. So we're making a pi bond, okay? The mechanism is called E1. Okay, so what do you think E stands for? Elimination. S of SN1 stood for substitution. Now we're eliminating. Okay, what does the 1 mean?
One step.
No. One molecule present in the rate determining step. It was a good try though. Okay, that is the most common thing that people get the 1s and the 2s mixed up, and that's why I go over it a lot. Okay, the more highly substituted double bond is favored. The more highly substituted. Okay, that's how many R groups are here. If you had 4 R groups, it would be considered tetrasubstituted. Okay, if you had only 3 R groups, it would be tri-substituted. See how it works? It's just how many R groups are on there. Okay? And rearrangements are possible. So what does that tell you? How do we rearrange? It's the same way we did before. You have to form a what? Carbocation. Okay? So this tells you that a carbocation is present in the mechanism. Okay, now I want you to notice that this reaction is facilitated by sulfuric acid or phosphoric acid. Okay, and as we go, we'll talk about why those acids. Why not HCl? Okay, we'll get there. Okay, you have to have the acid in there pretty much or it doesn't want to work. There's some unusual circumstances. Okay, so Zaitsev came up with this rule, and the rule, it's like he looked at a bunch of different reactions, and he said, look at this. Every time we do this, I noticed this. He noticed this, that when elimination could occur in more than one direction, the major product was the more highly substituted alkene. That's called Zaitsev's rule. So here would be your OH, okay? So if you have your OH here, do you see that there are going to be 3 possible places you can make a double bond? You can make one here with the blue, you can make one here with the green, and you could make one over this way with the pinky one. I don't know what color that is. Okay? So you could make a double bond this way, or this way. The one that will be favored is the one that makes the more highly substituted double bond. So if you look up here and you got blue, you got green, and you got that magenta color. What's magenta to me? Okay, which one do you think will give you the more highly substituted double bond? Okay, if you lose the leaving group and an H off of here, the blue, what will you get? We'll just do them all. You would get, here's the blue. Okay, that's this carbon over here, and then you got C, CH3, poor Zaitsev, if I'm going to write right on top of him. Okay, see what we did? We lost this and a blue hydrogen and made a double bond. Okay, so how substituted is that double bond?
I don't understand what you're asking about substituted, highly substituted.
Okay, look at this carbon here. How many R groups does it have on it? 1, 2. Look at this carbon here. How many R groups does it have on it? 1. So this is tri-substituted. It's substituted 3 times. Okay, if we do the green, okay, That means we're going to lose the leaving group and one of these hydrogens. And we're going to make a double bond there. Okay? So what will we get from the green? We'll get R, I'm going to write R2. P2, no. Man. Okay, so here's our new double bond right there. Okay, how substituted is that one? Since purple isn't a color. Okay, so we've got one R group on this carbon and a second R group on that carbon. The carbon that's below, how many R groups does that have on it? Right? Okay, it has two H's. So this one is di-substituted. Okay, so which one's winning right now for a major? Tri is winning right now. Okay, now we're going to do the other side. I guess I'll use red. That's the closest I got. Okay, so I'm going to lose this and that. Okay, so what am I going to get? I'm going to have R, C, double bond, C, CH3, CH2R. Okay, so how many R groups are on that double bond? You look at each double bond carbon in turn. This has 1, 2. This one has 1, 2.
Wait, why does that one count now?
Because it's a carbon.
Yeah, you didn't count this one down here.
Because that one has 2 hydrogens on it. You look at this carbon, and what does it have on it? 2 hydrogens. Yeah.
Why does that matter?
Because if it has more R groups on it, it's more highly substituted and it's more stable. And that's why the reaction favors that. They figured it out by running reactions and figuring out what was major. All you look at are the carbons of the double bond. You look at those 2 carbons. I feel like that's too dark. So here's a carbon. Here's a compound. Okay? This is called a di-substituted double bond. Okay? Because this carbon has 1 R group on it, and this carbon has 1 R group on it. Doesn't matter what they are, as long as they have a carbon there. Okay? So this is di-substituted. Okay? If you have this, it's going to be monosubstituted. It has 1 R group on it. Okay? You just look at the carbons of the double bond. Okay? Those are the only ones you look at. Okay? This has a carbon on it. This has 2 hydrogens. This has a hydrogen and a carbon. So it's monosubstituted. Is it making sense yet?
Okay, so the reason we didn't count the CH2 down at the bottom is because the C that the 2 hydrogens are attached to is part of the double bond.
Yes.
Okay.
Yes, you look at what's attached to that carbon. 2 hydrogens are attached. Right. This is an R group attached to that carbon. Okay? Is it making sense?
What is the beta carbon?
Okay, when you look at the carbon that has a leaving group, this is considered alpha. Okay? All the carbons that are next to that are beta. If you have a carbon over here, it would be gamma. Do we know our Greek alphabet? No? All you have to know is alpha, beta, gamma, delta, epsilon.
So if it's like,
That's all I know.
if it's more than 1 carbon away,
It's not going to work in this reaction.
I just meant it's called.
Yes, yes, it's called gamma. But for this reaction, we're looking at the leaving group and the carbon next to it, the neighboring carbon, the one right next door. Okay? You got it now? Okay, so look at this reaction. Okay, you're going to lose the OH. Okay, and what else? What do you think the major product is? Oh, well, gosh, I'm looking up there thinking, oh, we got almost 22. Okay. Yep, it's B. Okay. So when you take an alcohol plus acid, you do dehydration. Okay. So here's the OH. So where do we get the H from for the water? There are 7 H's up there. Which one? One from the methyls, okay? Right? Does everybody see you can't lose this one? It has to be next door. Okay? Does it matter which one? No, you're going to get the same product. So you're going to get okay? How substituted is that double bond? 1, what's that called? Mono. Okay, we got that figured out now? Okay, everybody see, it's this. It's not this. Okay, it's elimination. So you're going to lose water and make a double bond between 2 carbons. Okay, so look at this compound. This is a ring compound. Okay, we're going to go through the whole mechanism with this one. Okay, so here we have our alcohol. Here's our OH. Okay, and we're going to lose water. So where do you think the H will come from? Well, if it comes from up here, that gives us this one. Okay, and the other possibility is one of these. Do you see that this one and this one are the same? That if you drew this one like this, it's the same thing. It's just flipped. Okay. What's this, Caitlin?
There's like noises happening, sorry.
I know, I was hearing them too. I don't know why, because that building next door is closed, so. Maybe it's Jackie singing, you think?
I hope that's not her singing.
Okay, I don't know what I did. Okay, so which one of these do you think is major? The first one or the second one?
First,
Why?
more substitution.
It's more highly substituted. How substituted would you say that first compound is? Tri. There's a carbon here, here, and here. What else is here? Whoops, here. An H. Okay, so this one's tri-substituted. What is this one? How substituted is that one? I'm going to have to put these questions on the test. What? Di. Okay, the H's don't count. You look at the carbons of the double bond, how many R groups do they have? Okay. Okay, this reaction is called stereoselective. That means that there are possible products and one is formed more than the other, to the tune of 93 to 7. I mean, that's a big difference. Okay. And it follows Zaitsev's rule. When we say follows Zaitsev's rule, that means the more highly substituted double bond is favored. Okay? There are 3 steps to the mechanism. The first step is protonating the alcohol. Okay? The reason that occurs first is because it's the fastest. And what do we have in there? H2SO4, that is sulfuric acid. Acids like to donate protons, right? Okay, so that's the fastest thing that will happen first. Then we're going to lose water to form a carbocation. And then a base will remove a proton from the beta carbon to form the double bond. Do I have more words down? Okay, this is an E1 mechanism, and it works on primary and secondary alcohols. Okay, so we're going to write it all out, the whole thing. Okay. Don't I have like a blanky slide here? Yeah. So there's where we're starting and there's where we're ending. All we got to do is fill in the middle. That's it. Okay, so when you take sulfuric acid and you dissolve it in water, what do you get? Do you know? Do you remember? Sulfuric acid, it's in water. In fact, when you buy even concentrated sulfuric acid, it's a solution in water. Okay, it's like, what, 16 molar or something? I don't remember. I have to look that up. Not too many stuff in my brains. Okay, so what does it do? Almost as much as y'all have. It makes, have you heard of this? What is this? Hydronium ion. Okay, and what else? Isn't there something like HSO4 minus? Okay, so you can use hydronium ion for your acid. You don't have to draw out the Lewis structure of sulfuric acid. Do y'all know the Lewis structure of sulfuric acid? No. All right, well, let's draw it out then, just so you have it once, okay? Yeah, I do. What?
Sorry. I'm done, you know.
Okay, do you remember that sulfur breaks the octet rule? Remember that? That was the bane of the general chemistry, doing Lewis structures are the ones that broke the octet rule. I hated them. Just like y'all hate them. Yeah, not a biggie. It's okay. Okay, so we're going to protonate the oxygen of the alcohol. Okay, so looky here. These electrons are going to come over here and grab a proton. And then what happens to the electrons in this bond? Where do they go? To the O. Okay, so what do we have now? Remember, it's going to be one step at a time. Okay, so this is what didn't change, right? Okay, so now what changed? I made a bond from the oxygen to a what? Hydrogen. Okay, that's how it gets protonated. You're reaching out and grabbing a proton. Remember, you do not draw the arrow to show movement of the proton. You're always showing movement of electrons with arrows. Okay, and then what happened over here? What did I get? Water. Okay, I don't like that. That looks like it's positive and it's not. Whoops. Let's try that. Okay. Okay, so this O over here was positive. What is it now? Neutral. Does that make sense? Everybody agree that O is neutral? Okay, what about this O? It was neutral and now it's, wow, it's really positive. That is funny. I didn't know I was on that. It's really positive. Don't forget it. Okay. Okay, so that was step one. We protonated the alcohol. Okay, all that just to do that. Okay, what happens next? What did we say? We're going to form a carbocation. Okay, so in order to do that, we're going to lose something from this molecule. Does everybody see how there's water right there? Okay, we're going to lose that water. To lose the water, the electrons in that bond are going to go to the O. And what will happen to that O? It will become what? Neutral. Look at that, all this water. Okay, so what about the other part of the molecule now? This is what we didn't change, right? Okay, now what do we need? Okay, this carbon right here is positive. It's just a little positive. It's not giant positive like that. Okay? See how we got that? Notice it's only one arrow. It's only one arrow, y'all. Okay, now what is the difference between this and the product down there? A double bond. What else? It's lost a hydrogen because on these carbons there are two hydrogens. And over here on this carbon there is only one hydrogen. Okay? So what do we need to do? We need to lose one of those hydrogens. Okay? So because this thing is positive, these hydrogens are easy to remove. So the water is going to grab that proton and the electrons in that CH bond are going to go down there and make your double bond. Okay, and that's how we end up all the way over there. Okay, so this is our carbocation. Wow. Okay, so do you see the 3 steps? Okay, I got them up there. Okay, this is your reaction coordinate diagram. Okay, notice that there are 3 steps, so we're going to have how many mountains? 3 mountains. Okay, 1, 2, and 3. Okay, I'll explain the 2 colors over there in a minute. Okay, the first thing that happens is we protonate. Okay, this generally is exothermic, and you'll notice that this is lower than that. Okay, so this is exothermic and very easy. So your activation energy for this step is nice and low. Okay, so which step is the rate determining step? Step number 2, right? because we're forming that carbocation. That's how come. Okay, that's your little intermediate that's there. Okay, so your activation energy for the whole thing is here. Not quite sure what that is all about. Okay, so you're forming the carbocation should be the tallest mountain. Okay, then the third step is making the double bond and losing a proton. There were two possibilities. One was losing a hydrogen off of one of the carbons in the ring to make this compound. The other one was losing one of these hydrogens off the methyl to make this compound. Okay, well, which one was more stable? The tri-substituted double bond. So the path to get there, bless you, is the light blue path, and it's lower in energy. The molecules can easily do that more of the time. 93 to 7. Okay, now what are these things? Yeah, the transition states. Okay, so we're going to draw the 3 for the major product. Okay, so you've got the mechanism on your sheet, right? Y'all wrote it down. Okay, because you're going to want to have that. Okay, so transition state 1.
Can you go back?
Why?
Yeah. All
What are you missing?
Everything except for the 2 lines.
Oh, okay. Oh. So our first step is going to be going from the alcohol to the protonated alcohol. Okay, so you need to think about what bonds are forming and what bonds are breaking. Every time you write a transition state, you between 2 areas, 2 molecules, you think what is breaking and what is forming, and then you look for changes in charge. That's the easiest way to draw them. Okay, so in the first step, we have, are you okay, Caitlin?
Yeah.
Okay, we have, I'll tell you what, I'm going to do it like this so I can go across. Sorry if I'm messing up your notes. Okay. Okay, so here's our alcohol, and we're reacting it with the H3O plus from the sulfuric acid. Okay, so we're going to make a bond from this O to this H, right? So that in the transition state, remember, you're halfway, you're part way. Okay, so we're making this bond, and what are we doing to this bond over here? We're breaking it. So that's a partial bond. Okay, at the beginning, this O is neutral. At the end, it was plus. So what is the charge change? Partial plus, because it's gaining positive character. Okay, this O over here was plus at the beginning, and at the end, it was neutral. So it's losing. So in the losing positive charge. So in the transition state, this one is losing and this one is gaining. Okay, there is no way to show that one is adding and one is losing or whatever. We don't do that. We just write partial. Okay, everybody get that? That's a partial, right? Are they looking like partials or are they looking like 6s or G's?
I look like unfinished 8.
That's good. Unfinished 8 is good. Okay, now, what happened in step 2? Okay, what happened in this step? We went from being the protonated alcohol to the, right, and all we did was draw one arrow, remember? Okay, so, transition state number 2, the bond between the carbon and the water. Okay, this is where we're starting. Okay, so what are we doing? In here, we are breaking this bond, right? Okay, and then what else are we losing? The positive charge, right? At the end, the O was neutral. So what goes here? Partial positive. Okay, what happens to this carbon? It becomes positive, so it gets a partial positive. The transition state, remember that, in between. Okay, so that's our bond we're breaking. This carbon is gaining positive character. The O is losing it. Okay, now we got one more step. Okay, so what happens in the third step? And we're just going to do it for the more stable double bond. So what happens in the third step? We lose a, and form a double bond. Okay, so we're going to have, it really helps to draw that hydrogen in that you're losing. Okay, and where did the hydrogen go? It went to what? A water. So you're making a bond between this hydrogen and that O. Agree? Okay. And you are breaking a bond between this H and that C. Agree? What else are you making a bond between? This carbon and this carbon. So there's a little partial double bond there. Okay, so at the beginning, this carbon up here was positive. At the end, it was neutral. So it gets a partial positive. Who else gets a partial positive? The O, because it was neutral and now it is positive at the end of that step. See how to do them? Okay, sometimes, oh, I didn't put the 3, my bad. Sometimes they'll get drawn like this with square brackets around it. You probably noticed that in the book and stuff, that they like to do those. I'm not really hyper about them. If I ask you to draw them, just draw them. After you put square brackets. Okay? Is it making sense? Sort of. Vaguely. Oh my gosh. Oh, I gave myself lots of space to draw that. Okay, oh, one thing I did want to mention that I didn't is that at the end we formed H3O+. Okay, so a lot of times this reaction is called acid catalyzed because we start with acid and we make acid at the end. Okay, so it's acid catalyzed. That makes sense. When you have something that's catalyzed, sometimes the catalysts are things just like acid, but they're always going to be regenerated in your mechanism. Okay, that's called a tip. Is that what that is? Okay, so relative reactivity or ease of dehydration. Okay, the tertiary alcohols are going to be the alcohols that have a carbon with 3 R groups on it. Okay, secondary ones, the carbon of the OH has 2 R groups, and primary is this one. Okay, can you dehydrate this one?
No.
No, because there's only 1 carbon. To make a double bond, you got to have 2. Okay, so everybody see why methyl isn't even going to be in here. Okay, we can substitute on methyls, but we can't dehydrate or eliminate. Oh, I guess this is what I need. Okay, so this one is way faster than secondary, which is way faster than primary. Any idea why? What did we make in our mechanism, first of all? We made double bonds, but what other intermediate did we make? We made carbocations. What's the most stable carbocation? Okay. So, why don't you just do what I want? More stable carbocation. That's my little shorthand for carbocation because it's too long. Okay, but the other thing is the double bonds that are formed from these are going to be more highly substituted. That also makes it easier to dehydrate. The double bonds formed, I'm not quite sure what's in this box, are more, what? Oh, okay. Why is that on your page? Oh, well, that's nice. Okay. That all makes sense. Okay. Okay, so what is the major organic product for each of the following reactions? What do you think you're going to get from A? So we've got an alcohol, we've got H3PO4 and heat. Typically, these are all heated up, by the way, to help get that water to leave. Okay, so what will we get from that one? Where's he going? Okay, so this is an alcohol and an acid, so it's dehydration. Okay, so what happens? The acid's going to protonate the OH. You're going to lose water and make a carbocation. So what do you think we're going to do? What? Okay, we got there. What kind of carbocation is that one? Secondary. Can it become tertiary?
Why wouldn't you just form a double bond between those two?
You can, but that's not the major product.
Why? Highly substituted.
Because when one of those methyl groups moves, look what you get. Look what we get. Tertiary. So this was secondary, and this one's tertiary. Anytime that you can rearrange, you do it to make it more stable. Okay, now which hydrogen am I going to lose to make my double bond? Which one? I can lose one off the methyls, right? Or I can lose that one. That one, why? Because I'm going to get a double bond that is how substituted?
That's literally what I asked. I said, why can you not do that on the first? That's what I was.
I thought you said, why can't you just lose a hydrogen off the
No,
methyl?
when you're right here in the first step, I was saying, we just, that's what I was thinking to do.
This has an extra step. There's more steps in this one. Whenever you have a rearrangement, there's more steps. But yeah, the methyl moves. Anytime you make a carbocation in any mechanism, If something can move to make it more stable, it does it. Okay, so this is your major product. Okay, now what do you think it was that one down there? I need to put them on separate slides because there's not enough room. Okay, so you protonate the OH, and then what? What happens after you protonate the OH? You lose what? Water, and make a carbocation. Okay, now what do you want to do? You just want to make a double bond here, here. It doesn't do that. I mean, you can get a little bit of that, but you're going to get like hardly any.
Can we pull that one down?
Okay, what do you want to do?
Pull that, like that one,
This one?
the carbon, and pull it down. That labels.
Okay, remember that when you have a carbon that's plus, we move to that carbon. Okay? And the plus moves, which is what maybe you're trying to say. Okay? So what I'm going to do is I'm going to move the ring. The whole ring bond is going to move. Okay? Why would it do that? What can you tell me about this ring? It's how many carbons? 4. And when this moves, we now have a 5-membered ring, which is more stable. A 5-membered ring is more stable. 6 is the most, 5 is second. Okay, 4 is strained. Those angles in there are 90 degrees, right? They don't want to be 90. They want to be 109.5, right? Okay, now which hydrogen will you lose to make the double bond?
Where does the positive charge go? Does it stay on that?
It's on this carbon right there where I drew it. This carbon here, oh, wow, I didn't even know I could do that. Okay, this carbon right here is this one. Okay, I'll put that little dot there. Okay, this carbon, I'm going to change colors, right here is this one. And what does that one have on it? A methyl, the ring, and a H. Okay, I'm going to write that CH3. So what are we going to do? We're going to lose this H, because what is that going to give us for our double bond? How substituted? Tri-substituted. So we want the most stable carbocation, you want the most highly substituted double bond. Okay? Those are probably the 2 hardest ones. Okay, is it making sense? Okay, we'll do that one next time. You want me to go back? Right here? Okay.
Yeah, like 10 points.
Hey, look, I'm going to color it again. So this bond is now here. All right. See you on Friday.
They got chicken
Not the way
no chicken tacos. No
beat
chicken
you up,
tacos.
little girl.
They're taquitos, but like fried and fake, so I'm hyped. So what is your last name?
I think